We all live in two worlds, our traditional analog world and the new digital world. To bridge these worlds, we need to convert our speech and other analog data into the bits and bytes that controllers can handle. Today we are with Stuart to discuss the working and the specifications of analog to digital converters. Stuart, good morning.
Good morning, Victor.
Hope you're okay. Stuart, last time we met, we discussed transducers, energy into electricity, basically everything, speech, data. But today I would like to discuss with you how to transfer or how to convert analog data into digital data, analog to digital converter. How does that work?
Okay, well, let's step back from it for a moment and sort of get a larger view of it. We started last week, as you said, with transducers. In this case, we were talking about specifically microphones or things that acted like microphones. These will put out an analog electrical signal. Ideally, in a system, you go as quickly as possible from an analog signal into the digital domain, and then on the other end, as late as possible from the digital domain into whatever analog response that you're looking for. An analog to digital converter is the way of taking that electrical signal right from the beginning and turning it into a set of numbers that a computer, controller, what have you, can handle. Yeah. This is very important. I mean, in the old days, before we had such power in the digital domain, this would all be done analog. So, for example, we had talked about microphone arrays last week, where you might subtract or add signals from different microphones at different positions. This was done with things like operational amplifiers, resistors, capacitors, and so forth, all of the summing and subtracting. And there was, besides a lot of circuit complexity, there was a lot of error in things like that. These days, if we can get from that analog signal into a digital number very, very quickly, then at that point, all of the processing can be done with just simple addition and subtraction in the computer. Okay. And we know how well they do that.
You're mentioning as soon as possible get this analog data converted into digital data. Why is it important to have this as soon as possible? What sort of frequencies can we do? Because analog signals come in all sorts of frequencies, and values.
Okay, well, there's two questions there, both of which I think are very important. The first question is, why do it as soon as possible? An analog signal is corruptible. Things like noise, distortion, drift, thermal drift, things like that happen very readily with an analog signal. The same advantages that we saw when we went from things like magnetic tape or vinyl discs into compact discs, downloadable files, which is the absence of noise, perfect pitch stability, incorruptibility of the data, really. Those advantages also accrue when we're talking about embedded systems, when we're talking about things like smart speakers, IoT. So if we very, very quickly get into the digital domain, now we're just handling numbers. And again, that isn't necessarily perfect, but it's a lot easier to make perfect than taking various analog signals, combining them, subtracting them, adding them.
Yeah.
What have you.
And then,
now, the second question is the speed. Okay, and I think you had asked about this. The audio domain for most of what we're concerned with reaches to roughly 20 kilohertz. And someone my age, of course, 20 kilohertz is a dream. Lucky to get to 12 or 13. But if we assume worst case, and we've got very young female children raised in quiet environments, or people with really exceptional high frequency extension, then 20 kilohertz is sort of a reasonable upper limit.
Okay.
Now, because of the Shannon-Nyquist theorem, which I think most engineers are fairly familiar with, and if you want to capture perfectly accurately signals up to 20 kilohertz, then that means that your sampling rate, and we can talk about that a bit, has to be somewhere above 40 kilohertz. That's extremely easy to do these days. And whereas bandwidth may have been an issue 20, 30 years ago, these days it's trivial. I can buy analog to digital converters which will handle that entire frequency range for literally pennies.
Yeah, you're introducing a new term here, sampling rate.
Yes.
The sampling rate is quite essential in understanding how an analog to digital converter works.
Yes. Really, when we're trying to convert an analog signal into numbers, it's going to be a sampling. I mean, if you have, for example, a sine wave which is doing this in a more or less continuous fashion, what we're doing is picking points from it. And each point will say, okay, it happened at this time, there's a number associated with that, and it has this amplitude, and there's a number associated with that. So we're essentially getting pairs of numbers for each point along that wave. Now, the closer in time that those samples can be taken, the higher the bandwidth. That rate, that number of samples per second is the sample rate. I mentioned Shannon Nyquist before, and again, that's just one of those iron laws that in order to get a certain bandwidth, you have to have at a minimum twice the sample rate, which is twice that of the highest frequency you want to capture. Okay. Now, what's not intuitive, and I think a lot of people have issues with this because they just don't get it, is that even though it seems like, well, gee, I'm only capturing 2 points along the sine wave, how can I possibly reconstruct it? I seem to have lost a lot of data in there, but no, you really can construct that perfectly. I mean, the math is solid, the experimental verification is absolutely solid. So we have to sometimes give up intuition and go with what the mathematics tells us.
Yeah. Great. Now, if you do the sampling and you actually end up with digital numbers on what the original analog value was, then the next step is to get it into a controller. What is coming out of an ADC? Is it a stream of bits, or are we talking about bytes?
Well, there are different sorts of outputs, and again, it depends on the system, the overall system, what sort of format you want them in. If you want something which is in what's called an I2S format, that can be done. It can be done in parallel, in series. So, for example, you can have a set of paired numbers coming out one after another, like train. They can also be coming out in parallel streams, so various numbers, again, depending on what sort of processing you want to do on the other end. But the key is, no matter how those numbers are coming out, they're coming out as numbers, which means incorruptible. And the only thing which is really important here is how fast are you sampling, and then how accurately in terms of amplitude that we're sampling. We sort of skipped over that, but that's also an important aspect of it. Each sample is 2 numbers, the point in time and the amplitude. Okay. The point in time is based on the sample rate. This is what we were mentioning before. The number of bits tells you how finely you can divide along the voltage axis or along the amplitude.
Yeah.
How tight are your cuts? The greater the number of bits, the more tightly you've got that number. Now, it then gets down to what do you really need? More bits means more data that has to be handled, maybe potentially more expense. Yeah. But at the same time, you get a better signal-to-noise ratio, less noise from that AD process, and a little bit better accuracy. How much do you need? It depends very much on the application. Somebody who's doing high-resolution audio might want 24 bits. Okay. Someone who's doing simple voice activation, 8 bits will be just fine. Okay.
So they come in different varieties as well. What is your preferred, if you're an audio engineer yourself, if you have to choose for an ADC, what is your preferred sampling or your bit rate?
It depends on what it is I'm doing. Again, it's all very application specific. If there was one best, that's of course what everybody would be doing.
Yeah.
I do music recording a lot, and for music recording, I tend to use 24 bits and a sample rate of either 96 kilohertz or 192 kilohertz. Not that you need that much bandwidth, but as long as I can get it, and it doesn't cost me anything.
It doesn't cost extra.
I can do that. Right now, in terms of the bit level, here there's going to be a difference again between sort of playback and recording. For recording, if I'm recording a musician, I can't always make sure that I'm capturing his entire dynamic range perfectly. My level might be a little too high, it might be a little too low. When it comes time for me to adjust the recording, I may lose some bits. So if I want at the end to have a good solid 16-bit recording, then I have sort of 8 bits for safety when I do 24 bits. I don't think in the real world anyone can really hear, if you match the levels, the difference between a 24-bit and a 16-bit playback. But in the recording sense, that can be very important, again, just because the levels are less certain.
Sure. Now, you're touching on a sort of sensitive area here as well, in the audio world, I think. So what is your conclusion? What is your experience with this?
I've done some testing, and of course other people have and have published it, where I put things like a 16-bit 44 kilohertz A to D, and then the reverse digital analog system into my analog chain, switched them in and out, and I couldn't hear a difference, and no one I tried it with could hear a difference either. I can't say that means that there is no one on the planet Earth who would be able to detect this. But
can you measure it? Yeah. Can you measure the difference? Can you measure?
Absolutely.
Yeah. So if you putting in an audio precision in between, it will actually say, okay, this is an audio signal as it is, and this is a digital converted signal.
Generally, again, if your analog noise floor is fairly high, then it may not be able to detect it, depending on the bandwidth of the signal. It might be able to detect it in the sense that, well, we've got that bandwidth cutoff because of the Shannon-Nyquist theorem that I mentioned before. But again, most analog signals just don't, for audio that is, don't have much energy up there, and it might be a difficult thing to detect. Yeah. Now, if I have a super low analog noise floor, then I might be able to detect the difference. A 16-bit noise floor will be something like 96 dB down from the highest signal, whereas a 24-bit is going to be quite a bit below that. And if I have a magic analog system that has a noise floor below that 96 dB, then I could potentially tell the difference. I don't know of any practical analog systems that are that quiet, which is again one of the reasons we moved over to digital about 30 years ago or so.
Yeah. Just going back to the product you mentioned last time, which is basically a transducer array with a set of microphones, with the possibility to actually detect a sort of location where the sound is. What sort of ADCs are you using in this project?
For this one, I'm actually using a fairly simple system. I have on hand some 16-bit devices which are being sampled at 48 kilohertz. I could use a higher bit rate, I could use higher bandwidth, but I happen to have these on hand. Okay. They're, for the purpose of what I'm doing here, they're far and away good enough. From a commercial point of view, again, these things cost pennies. So if you have an ADC for each microphone, the difference between having, say, 16-bit 48 kilohertz and having 24-bit 96 kilohertz might be the difference between having 25 cents worth of these things and 30 cents worth of these things.
So for everyone, So for everyone interested in starting and getting familiar with ADCs, it's really relatively cheap to start off with. So it won't cost you any money. Is it difficult to handle? Is it what sort of level do you need to have to start actually to working with ADCs?
Well, there's going to be a lot of tricks because you're now taking a single device, which is mixing signals in the digital domain with signals in the analog domain. And you don't want those interfering. You don't want, for example, the digital signals to cause noise on the analog side, because the ADC is dumb. It doesn't know that, oh, this other stuff on here, these little spikes, these little bleeps, these are noise. It doesn't know that. It's just going to very faithfully convert them. So things like board layouts, power routing, things like that are fairly important.
Yeah.
The second thing, and again, I kind of glided past this, is bandwidth limitation. If I need to limit the bandwidth to 1/2 or less of the sampling frequency, then I have to have some sort of analog circuit ahead of the ADC to make sure that signals that have higher frequencies than that aren't put into the ADC. If that happens, we have a type of distortion known as aliasing that can occur. So there's sort of two ends of that. You've got the signal conditioning, filtering. You've got the layout, which means routing of signals so that digital and analog signals don't interfere with one another. And then finally, the analog to digital converter has a reference voltage. Everything that it's measuring is with respect to the reference voltage. So if I have, say, a 2-volt reference, then if I put in a 1-volt signal, it'll say, that's minus 16 volt, whatever that is, or half the number in the code. Now, if that reference signal starts moving around, again, the ADC is dumb. It doesn't know that, my reference signal is moving around. What it knows is how does the signal that I'm seeing compare to that reference signal. So that also has to be fairly tightly controlled.
Okay.
So it isn't that anything is particularly difficult, it's just there's a lot of details that need to be attended to. Fortunately, this is such a well worked out field that it's very, very easy to learn from the mistakes everyone else has made. And with a bit of work in the lab and some reading into literature, it's not hard at all to build such a system.
Okay. Thank you very much for the introduction, and hope to catch up with you in the next episode.
Thank you so much. Fascinating talking with you.
Excellent. Thanks very much.
Bye.
Bye-bye.